Throughout our investigation of the layers of Earth and the formation of features on Earth's surface, one material has been at the foundation of it all: minerals. Let's take a look at these beautiful structures to learn more about how they contribute to Earth's surface. The crust, or lithosphere, is made up of two things: minerals and rocks. Given that rocks are just mixtures of different kinds of minerals, we can really say that the land, at its simplest, is made up of dozens of different kinds of minerals. But what is a mineral exactly? Let's take a closer look. Do you remember back to 7th grade when we talked about living things? And we said that all living things had to have those 6 characteristics, like made of cells, obtain and use energy, etc., etc. Well, non-living things like minerals have a similar checklist that they use to determine their identity. Minerals have 4 qualities. They are naturally formed, inorganic, meaning they're non-living, they're solid, and have a definite crystalline structure. If you can say yes to all 4 of those characteristics, then you have a mineral. If it doesn't satisfy even one of those qualities, it is not a mineral, it's something else. So what are minerals made of? Minerals are either pure elements like a diamond, which is pure carbon, or gold or silver, both of which are metals, or it's a compound, something like quartz, which has a chemical formula of SiO2, or silicon dioxide. If you remember back to your days in chemistry, both elements and compounds are considered pure substances because they can't be broken down into simpler substances by physical means. Even though quartz has more than one element in it, both silicon and oxygen, it's still a pure substance because it can't be separated into silicon and oxygen by physical means. Those two elements are bonded together, so it would have to undergo a chemical reaction to change. But where do minerals come from? They form in one of two ways: either by evaporating from a solution of materials dissolved in a liquid, think about salt evaporating from seawater, or from cooling of molten material. Minerals that form from evaporation on the surface of Earth are very common as Earth contains a lot of water. Water on the surface contains a lot of minerals that are dissolved in it. When water evaporates as a natural part of the water cycle, it leaves behind crystals of minerals. This is not only true for salt, like we mentioned before, but also other minerals like calcium. This picture at the bottom, you can see those white structures. They're large calcium deposits from Mono Lake in California. They can only be seen when the water level is low enough in the lake and it drops, but they're often hidden below the surface. There are also minerals that form from evaporation below Earth's surface. Deep underground, hot magma heats nearby underground water. This water reacts with the rocks around it, causing minerals to dissolve into the water. It flows through the cracks and spaces in the surrounding rock, and as water evaporates, it leaves behind those deposits of solid minerals called veins. This top picture here shows bright white lines of a mineral called quartz within the rock. But this is the same way that gold forms veins in an earth, just like prospectors look for, or beryl, also known as aquamarine. If you see prospectors looking for those sorts of gemstones, they form in veins due to evaporation. One nifty thing that can happen is those dissolved minerals will find a large open space underground to seep into and form large crystals within that cavity. Those are called geodes. You may have gotten a small geode at a fair to crack open. They're pretty tough, but once they crack open, they're really beautiful. This picture is an amethyst geode, so it has that really pretty purple color, but they come in all sorts of colors. Minerals can also form from cooling lava and magma. So from our study of volcanoes, you may remember that there is a difference between magma and lava, and it's all about location. Magma is melted rock inside Earth, so below the surface. When it cools, and it happens very slowly, this gives all the minerals in that mixture a long time to form large crystals, which can easily be seen with the naked eye. If you look at the picture on the top right, you can clearly see the difference between the pink feldspar crystals and the white quartz crystals. Lava, on the other hand, is molten rock that is above Earth's surface, usually coming out of a volcano or a crack from divergent plates, and therefore it cools really quickly, leaving the minerals a very little time to form large crystals. As a result, often the crystals are way too small to see with your naked eye. But if you put a thin section under a microscope, you can clearly see that there are mineral crystals in there. Look at that picture at the bottom that has that dark sample. You can see little white crystals amongst the dark material, but that same material, if you took a thin slice and put it under the microscope, you can see that it's made up of a huge matrix of crystals. They're just all very, very tiny. So this is just a quick graphic organizer. Use this to organize your thinking as we discuss minerals further. On the left-hand side, we have minerals formed from evaporation, both above ground and below ground in veins. Or we have minerals formed from cooling of molten material. The lava above ground that gives us very small crystals, and the magma below ground that gives us much larger crystals. Both processes can happen above and below the surface and will result in different kinds of minerals, which gives us the diversity that we have. Minerals are classified into two main groups based on what they're made of: silicates and non-silicates. Silicate minerals like quartz and mica contain silicon and oxygen and one or more metals from the periodic table. So quartz has a chemical formula of SiO2, silicon and oxygen. Feldspar has a formula of NaAlSi3O8, so sodium, aluminum, silicon, and oxygen. Now you know why we call it feldspar. It's much easier to say. It'd be quite a mouthful if we used its whole chemical formula. Non-silicate minerals don't contain silicon and oxygen together. They may have oxygen, but not together with silicon. As you might imagine, this makes up quite a large diversity of minerals. So there are several subgroups that are formed. Things like native elements, which contain only one pure element of minerals, like gold, diamonds, silver, aluminum. Or you may have another group, like my personal favorite, the halides. These are salts that form from elements from the halogen group, group 7, like fluorine and chlorine, when they bond with elements from groups 1 and 2, like sodium or calcium. I don't need you to memorize these subgroups, but I do want you to recognize that there's a huge number of different kinds of minerals that would result from all of these different combinations of elements and compounds. It's a lot for scientists to keep track of, and it's a lot for us to investigate in the future. So we're going to need some way to identify them easily. Knowing how many minerals are within Earth's crust, it leads us to the question, how can I identify them? Scientists measure the physical properties of minerals like color, streak, fracture, density, and others to determine the identity of a mineral. But be careful here. Using just one property can lead you down a very wrong path. Let's look at an example on the next slide. The same mineral could come in a variety of different colors, like the fluorite samples you see below. I see brown, blue, purple, green, and pink. If I were to just use color to identify my sample, I may mistakenly identify green fluorite as olivine or blue fluorite as beryl, as they are the same color. Color can help us narrow down a mineral's identity, but it's not a good single indicator to the mineral's true identity. One feature that we use to help us is called the luster. It's really how much light is reflected by the surface of the mineral. Think about it like shininess versus dullness. If a mineral is very shiny, like a chrome bumper on a car, you'd call that metallic. If it's sort of shiny, almost like a glassy surface, you'd call it submetallic. Sub meaning below or under. So it's not quite fully metallic, just below that. However, if it doesn't reflect light at all, like a piece of chalk, which yes, is a mineral, then you'd call it non-metallic. Sometimes you'll see that listed as dull, but it really means the same thing. Another physical feature that we use is called the mineral streak. It's very silly, get your giggles out. It gets the name for the process done to see that property. Minerals can be ground into a fine powder by running them along an unglazed porcelain plate. This is rough and acts almost like sandpaper, which causes the mineral to leave a streak of powder behind. The color of this streak is sometimes unexpected. If you look at the bottom picture, you can see that the black rock or mineral makes a rusty colored streak, while the fool's gold or pyrite makes a black streak. You would expect those minerals to have the reverse effect, and they're actually a clue to their identity. The way a mineral breaks will also help us determine its identity. If a mineral has smooth, flat surfaces, we say it breaks with cleavage. To cleave means to cut, so it almost looks like it's been chopped or cut along sharp edges. On the other hand, if the mineral has curved or irregularly shaped surfaces, we say it breaks with fracture. The piece of obsidian in the bottom right-hand corner is a great example of fracture. You can even see the curved lines where it broke away from the material. Materials like obsidian were used to make arrowheads because when you strike the mineral in the correct way, it makes almost like a serrated edge on a knife, those curved, sharp lines, causing it to have very sharp edges. One of the most common tests used to start the mineral identification process is called the hardness test. It measures the mineral's resistance to being scratched. Using a scale called Mohs hardness scale, you use known objects like your fingernail, a steel file, a piece of glass, and other such materials with a known hardness to scratch the mineral to determine if they are softer or harder than that. For example, your fingernail has a known hardness of 2.5 on the Mohs scale. If you rub a mineral across the top of your fingernail and it doesn't scratch your nail, that means it is softer than your nail. It doesn't have the ability to scratch your nail, so you know that it's not harder than your nail. That would mean it would have a hardness of less than 2.5, like gypsum or talc. If you combine that observation with how it breaks, its color, and its streak, you are really starting to narrow down its identity and getting it closer to accurate. Mohs hardness scale uses what we call index minerals. These 10 minerals, talc, gypsum, calcite, fluorite, apatite, orthoclase, sometimes feldspar is in there, quartz, topaz or beryl, corundum, and diamond. These 10 minerals have known hardnesses that fall exactly at 1, 2, 3, 4, etc. We have samples of all of these at school except for diamonds. Those are a little too pricey to keep around, but a corundum is at a 9, which is really, really hard and will be harder than most of the mineral samples that we'll see. If you have a pure enough sample, you can also use density to determine the mineral's identity. Each mineral has its own unique density, so it can be a great tool for identification if that sample is pure. Given that minerals are often very irregular in shape, you have to use the displacement method to find volume and then a balance to find mass. A simple division problem of mass divided by volume gets you density, which you can compare to a chart of known densities to help you find the identification of your mineral. Finally, there are some minerals that have some very unique properties. For example, fluorite is infamous for its ability to glow or fluoresce brightly under UV light. That's where it's got its name. Other minerals like magnetite are, you guessed it, magnetic, or things like calcite may react with weak acids and fizz. One property that we never test in school for safety reasons is radioactivity, but uranium and radium are two minerals that would send that Geiger counter off the charts. One of my favorite special properties is taste. All of the halides, like halite, are very salty. They are actual chemical salts, and you can taste the salt very clearly in those. We never taste in science class, but if you're out in nature, you certainly have the opportunity to do that. As you can see here, the minerals that may fluoresce are often very boring to look at in the normal light of day. But like many of their features, they just take the right tools, a little skill, and quality observations to see the beauty that lies underneath.